All right, we'll do the quiz at the end of class. We're in the middle of working through a problem. So from last time, we had this problem where we have these two pins. And a structure like that, and there's 1,000 Newton force down and 1,000 Newton force to the left. And these two angles are 30 degrees. And the lengths are each 2 meters. And we want to calculate the internal loads. First, we want to do it neglecting the weights. Well, we already did it. Neglecting the weights. And then second, we want to do it with the weights included, and we're assuming that these masses are kind of small compared to these, the weights are small compared to those forces. Otherwise, it wouldn't make any sense to neglect these weights for part A. But for the second part, we're going to assume that the masses are both 10 kilograms. And for part A, so if you neglect the weight, then each of these bodies is a 2-force member, and you end up with each body in pure tension or compression. In this case, they were both in tension. And we got, for member 1, a tension of 422. And then the other two were both just zeros. That has to be the case if you have 2 force members. You can't ever have shear forces or bending moments. And for the second member, the one on the right, we had internal tension of 1577. And then these two are zeros. Okay, so those are the internal loads. If we neglect the weights. And all you can get is tension and compression in that case. We use the truss simplification to calculate the external loads. Then we switch to part B, and we are at the point, so we calculated the external loads on each body, and we got this. Negative 450. I'm going to keep significant figures since we're still going with this stuff. Positive 309.42. And over here, 450.95. Negative 211.32. And then the weight force, which is a distributed load of 49.05 newtons per meter. And then the member on the right, we have negative 1450.95, negative 788.68. And on the right side, positive 1450.95, positive 886.78, and then the distributed load due to the weight. Okay, that's all for today. No, just kidding. Okay, so now we have to calculate the internal loads. And the first step is expressing these in a coordinate system with the x-axis along the long axis of the beam. So let's start with member 1, this one. And we want to, I mean, you could use a coordinate system. There are always two orientations of the coordinate system with the x-axis along the long axis. In this case, I mean, I think everyone would probably just use this, you know. Of course, you could use this one, and, you know, the answers would mean the same thing, even though the functions would look different. Okay, let's start by re-expressing all of these loads in a coordinate system like this. So take a second and see if you can okay, so there's just a single cut. This is for all x's between 0 and 2. We have a force on the left of negative 545.25, 42.49. The horizontal distributed load produces a force of 24.525 times x. And the vertical one is a downward force of 42.48 x. Those are both at the midpoint, so x over 2 from the end. And then we have the internal loads. Newton's second law says negative 545.25, 42.49 plus 24.525x negative 42.48x plus t negative v is zeros. And so your internal tension is negative 24.525x plus 545.25. Your internal shear force is negative 42.48x plus 42.49. And now the moments. This is my about point over here on the left end. The horizontal distributed load doesn't produce a moment. The moment arm for the vertical distributed load force is x over 2, and that's a clockwise rotation. So we have negative x over 2 times that force of 42.48x plus m minus vx is equal to 0. So m is equal to 21.24 x squared minus 42.48 x squared plus 42.49 x. And combine the squared terms and you get m is equal to negative 21.24 x squared plus 42.49 x. Anybody have any questions about that calculation? Okay, so let's graph it and look at what we have compared to the case where we ignored those, fairly small masses. So for the internal tension, we have a function of, at x equals 0, we're at 545. At x equals 2, we're at about, about 500. 545.25 minus so 496.2. So you get a little bit of a diagonal force, but mostly it hovers around 500. For the shear force, you have a value of positive 42.49 so I'll call that positive 42. And then it crosses 0 at the midpoint, and then at the right end point, it's at negative 42.49. So these are really small forces, but you get this, little diagonal thing. And then for the bending moment, if you plug in x equals 0, you get a value of 0. If you plug in x equals 1, you get a value of, this small thing, 21.24. And if you plug in x equals 2, you get 0 again. And this is a, whoops, I missed. This is a very small parabola. So compare that to the answers we got before. The v and m before were zeros. Now we have these small values, but they do fluctuate as you go. And for the internal tension, before we got 422. Well, now we get a bigger tension than that the whole time, but it goes from, it fluctuates a little bit as you go. So you can see, you can get, I chose masses that were maybe kind of on the edge of what you would want to treat as just neglecting the weight. the weight forces were about a tenth of the size of those applied external loads. So you can see, I mean, you get meaningful answers from treating it as if the weights aren't there, but you miss some stuff in the tension, and you miss a little bit of stuff going on, you know, a little bit of more complicated stuff going on. And of course, like the bigger the weights are compared to those external loads, the more important information you lose by treating it as having no weight. The benefit is it took us, you know, a fraction of the time to do it when we treated it as a truss. Okay, let's do the other member. So, well, let's just go all the way through it this time. So why don't you just go all the way, transform the coordinate system, calculate the internal loads, and then we'll just compare. So we can get this done and then do the quiz. All right, so for member 2, you rotate the coordinate system positive 30 degrees. And so we end up with a body like this. On the left end point, we have negative 1650.9, 42.46. On the right end, we have positive 1699.95 and positive 42.50. And for horizontal distributed load, you got 24.525 newtons per meter to the left. And then you have a downward one of 42.48. And again, it's just one cut. So for all x values 0 to 2. So you have the force at the end point of negative 1650.90, positive 42.46. Now you can represent that horizontal distributed load as a point force to the left of 24.525x. And the vertical one, 42.48x. And then TVM. And so Newton's second law says negative 1650.90, positive 42.46. Plus negative 24.525x, negative 42.48x, plus T negative V. And so internal tension is positive 24.525x plus 1650.90. Shear force is negative 42.48x plus 42.46. And the moment about the left end, we have negative x over 2 times 42.48x plus m minus vx is equal to 0. And so m is equal to negative 21.24x squared plus 42.46x. We didn't check the derivative relationships on body 1, but they still have to hold. You can see here dm dx is equal to v. dv dx, negative dv dx, is equal to the downward distributed load. We also have this new one that maybe you've noticed, or maybe you're too bored to notice, but dt dx has to be equal to that horizontal distributed load. Okay? And all those work, so we feel pretty confident about this. There's still stuff that can go wrong, but feel better about this. And I don't know, I'm not going to draw those, but you see basically the same story. Like, it kind of roughly is shown by treating the weights as 0, but you're missing some stuff. Any questions about that? Okay. All right, let's do the quiz.